we present our work, Enhancing Generalizable 6D Pose Tracking of an Inch-Hand Object with Tactile Sensing. We track the 6D poses of an object held and manipulated by the robot hand, which can be visualized as 3D bounding boxes. We focus on a generalizable 6D pose tracking setup, where the object to be tracked is a novel one without 3D instance model given. In human-robot interaction or assembly tasks such as peg hole insertion, robots need to accurately perceive object motion to complete the task. However, the proprioception ability of robots is limited, especially in complex operations such as peg hole insertion, where the object's in-hand pose constantly changes due to collision with the environment. Therefore, in-hand object pose tracking is necessary to improve the accuracy and efficiency of robot manipulation. We present Tactile, a tactile enhanced generalizable 6D pose tracking design, which utilizes tactile sensing to enhance generalizable visual tracking. Let's have a look at our method. Given visual signals, we leverage a generalizable 6D pose tracker to acquire object pose hypotheses. Marker flows can be detected from consecutive tactile images. When a tactile sensor is in contact with an object, the contact area of the sensor surface sticks to the object and moves simultaneously before a slip occurs. Therefore, we could measure the contact points' positions and velocities from the marker flows. Then we could estimate the object velocities using a kinematic optimization strategy. When the in-hand object slips on the sensor surface, the contact regions on the object change rapidly. Thus, contact point information of tactile sensors could become unreliable. We thus train a ResNet as a slippage estimator to predict velocities. Then we integrate the object's hypothesized poses and kinematic states using a geometric kinematic optimization strategy to predict object poses, and utilize the result to help subsequent tracking. To examine the effectiveness of Tactile, we curate a real dataset due to the lack of large-scale datasets supporting our research. Here shows our data capturing system, including the in-hand object, the tactile sensors, the visual sensor, the robot arm, and the motion capture suite. We apply various motions to the object to reflect different tracking challenges. We employ mainly 4 data capturing schemes, where the robot arm is stationary or moving, and the object has minor or severe in-hand motion. We collect 200 videos among 17 object instances spanning 5 categories. The system captures the visual tactile signals and object pose at approximately 20 fps, and each video contains 401 frames. Our dataset provides visual RGBD images, object segmentation masks, tactile RGB in-depth images, object poses, camera intrinsics and extrinsics, and we hope our dataset could facilitate future research on generalizable visual tactile in-hand object tracking. We show the comparison between our method and the corresponding generalizable visual tracker. Green bounding boxes indicate ground truth poses, while red ones indicate estimated poses. Results show that Tactile boosts generalizable trackers on real data. We test on several object categories, with Tactile demonstrating significant improvements. Tactile produces more stable tracking results while the baseline methods lose track. Quantitative results show that Tactile significantly decreases mean rotation and translation error, and elevates 5° 5mm metric on all object categories consistently. Tactile is a plug-and-play technique that boosts various generalizable trackers. Besides bundle track, a key point-based method, Tactile also boosts Captra, a regression-based generalizable visual pose tracker. Tactile is robust to initial pose error. Tactile achieves much higher accuracy than the baseline when Gaussian noise is added to the initial pose. Tactile also boosts various generalizable trackers in simulation. Thanks for your attention.